As you may already be finding out, our IBET project is full of challenges and opportunities. So as we prepare to dive into data analysis of our data sets, I want you to think of these skills in a larger context of data science. So data science involves data processing, statistics, machine learning, visualization, and big data. We're going to focus on these three for our project, and today we'll look at statistics, specifically hypothesis testing. So our goal is to understand null hypotheses and this pesky word that we often see in papers, significant or significance. My favorite analogy for null hypotheses is that scientists are like jurors. So scientists believe the null hypothesis of no difference between their treatment groups is true until they prove it is not true, just like jurors are supposed to believe innocent until proven guilty. Scientists must look at the data from one experiment with a limited set of conditions, so maybe time or equipment or cost was limiting. You can't gather all the data of nature, you sample. And in a courtroom, a case is limited to evidence collected. When hypothesis testing, there are only two outcomes. The null hypothesis is rejected, or there is not enough evidence, so we fail to reject it. Note that we don't talk about the null hypothesis being true, just like jurors don't talk about someone being innocent. A juror would say guilty or not guilty. So we presume innocence, but we say not guilty. We might presume our null hypothesis of no difference is true, but we're going to say we fail to reject the null. We never say it's true because we can't show it's true. This can be tricky because science students aren't always the best with using a lot of finesse around their word choice and language choices. So we just have to be really careful, right? And this is the take-home message. We reject our null hypothesis if our results are statistically significant. Please put that word statistically in there because we don't want to assume that results that are not statistically significant aren't meaningful in some way, right? And sometimes when we think of significance, we think of it being meaningful, but something that is not statistically significant could still teach us something about nature. When papers talk about statistical significance, you may and probably have seen them mention p-values. P-values measure the chance that random sampling would lead to that difference if the null hypothesis were true. So if you don't have a null hypothesis, you cannot have a p-value. Let's say I have two bags full of identical numbers. Maybe those numbers are test scores or something like that. I randomly sample each bag by drawing out a handful of numbers. Now remember, these two bags were full of identical numbers, but I'm just drawing out a sample. I compare those numbers with the t-test, and I calculate a p-value. We know that the bags have the exact same numbers. There really is no difference. We also know that each sample will likely be different, even if we do this dozens of times, right? If we put enough numbers in the bag and we draw out, a small sample, maybe 10 or 15%, those samples are going to be different each time. However, when we run this test, and approximately 1 out of 20 times, our p-value, we should calculate a p-value of less than 0.05 because 0.05 means that in 5 out of 100 or 1 out of 20 experiments, when the null is true, right, there's no difference, you will still find enough difference between your samples to generate a p-value of less than 0.05. Every time we repeat the sampling process, we'll get a different p-value. Thus, p-value, the smaller the p-value, the more extreme the level of significance. So here's just a handy table to help keep that straight. So greater than 0.05 is not significant. And then we start to get into more and more highly significant levels of our p-value, right? It's less and less likely that result, that difference between our two sets of numbers, would have happened if our two samples represented populations that were really not different from each other. Now, maybe you're seeing some, inherent problems here, right? Because p-values can be wrong. They may not represent what is truly happening in our experiment or between these populations or groups that we're trying to test. So reproducing the experiment could easily produce different results, and that could be used to throw doubt on the original experiment or the the reproduced experiment. Or you could just reproduce the experiment often enough that eventually you get a significant result, right? That's incredibly problematic. This is so common, these, ways around and ways of manipulating numbers, that there is a name for it now, and that's p-hacking. So p-hacking might involve analyzing many subsets of big data until you get a significant result, right? It's very easy to pull out subsets now. It's very easy to run multiple analyses, but then you only report those that are significant. That's highly unethical. But when we look at studies, we see they've done analyses, right? And they've seen that a kind of weirdly, oddly large number of studies have p-values reported that are like just below the threshold of 0.05, which is a little fishy, right? You should see p-values should vary widely, there's nothing incredibly magic about that 0.05 number, except it's the kind of conventional accepted threshold for significance. So here's my take-home message for you. Please, please, please do your research and know before you begin to analyze your data what you are trying to analyze and why you are looking for those differences in the first place, right? Don't just go stumbling into the dark and happen to produce a significant result because someone is going to be intelligent enough, we hope, to question and call you on it, right? Because that's good for the entire scientific community. So you already heard me talk about this magic 0.05 number, right? What is that? That's our traditional alpha value. The researcher chooses the alpha value at the beginning of the experiment. It has to do with setting your chances of error, such as your likelihood of rejecting the null hypothesis, even if it's true. So in our first analogy, that's like the probability of saying an innocent man is guilty. It's a false positive, right? You don't want errors. In this table, I've set our alpha to 0.05, and I'm pretending that we really know if our two groups are truly different or not. So in an experiment, we don't know. We're relying on our testing and inferences to find out. But for my example, let's pretend we know. If there's no errors and our samples represented our populations well, the testing outcome will be below 5% when there's a difference or above 5% when there's no difference. A false positive is getting a small p-value when there really is no difference. This is saying some difference exists when it doesn't. A false negative is getting a large p-value when there actually is a difference, right? So that means you missed communicating a potentially interesting piece of information. So that could be a difference or an association or a correlation. There are many stats tests and they interpret numbers in similar ways, like with that outcome of a p-value, even when they're testing for differences, something different. So a difference or an association or a correlation. A good study design and sampling methods is going to minimize your chance of error, but maybe you want to be more sure that there's a true difference in your groups. So in this sample, I set a smaller alpha value. So in this case, I'm less likely to get a false positive, but I'm also more likely to throw out those potentially interesting results. So since we don't have anything high stakes like human life or health on the line in our projects, we're going to stick with that traditional alpha of 0.05. So now we know how to compare a p-value to an alpha value, but where on earth do p-values come from? So you'll have to forgive me for an incredibly brief and simplified answer because all of these tests kind of need to be learned separately and with practice. But each statistical test is going to generate a test statistic, and that's going to be some value after you plug your data into a formula. So that's going to be like your t-value, your f-value, your chi-square value. If your test statistic is compared to a critical value, and that critical value is based on your alpha value and your sample size, it may be below the test statistic. So you got a big test statistic, small critical value means a small p-value, smaller than your alpha, and you reject the null. If your critical value is above the test statistic, so you had a small test statistic and a big critical value, then your p is bigger than your alpha and you fail to reject the null. So that comparison of p to alpha is a little bit of the review from the last slide, but there's another way to look at this. So the critical value is like a threshold value. If your test statistic is greater than that critical value, then your p-value will be less than your alpha. You have found statistical significance and you reject your null. If your test value is below the critical value, you failed to cross that threshold and you fail to reject the null. So for me, it's a little easier to visualize this way. There are more nuances to hypothesis testing than I could ever teach you in one YouTube intro video. So I really recommend you check out other resources, especially if you really want to dig into it. There's a great book by Harvey Moltulski called Intuitive Biostatistics, and it's all about understanding the values in papers, not actually making the calculations yourself, because as scientists, we're going to spend a whole lot more time actually reading and trying to interpret papers than we actually will writing them. But hopefully you're doing both. That's all for this time. Thanks for sticking with me to the end.